Hi everyone, this is second part and we will continue with this example, which is again about fundamental theorem of calculus part 1. So let's see what kind of limit is this. If you insert 0 here, then you are taking integral from 0 to 0, which is 0, right? 0. And at the denominator, you have another 0. This is an indeterminate form. Sorry, I couldn't write it. Indeterminate form. To which you can apply L'Hopital's rule directly, right? Apply L'Hopital's rule. So let's apply it. L'Hopital's rule. How do you apply L'Hopital's rule? You take the derivative of the numerator, sine x t cubed dt, and you take the derivative of the denominator separately, right? So I took the derivative of the denominator like that. And what about the derivative of the numerator here? Of course, you will apply FTC part 1 because integral is derivated. So in this order, this is FTC part 1. What you should do is you will insert this function to the variable t here. So what we have is the following. Limit as x goes to 0. Sine x for t, I am inserting the variable, the function that I see here, so x cubed. Be careful, you are inserting for t, not x. So t is, for t, I write x. Then I need to multiply with the derivative of this function, which is 1, 5x to the power 4. So what we have is x goes to 0, sine x to the power 4, 5 times x to the power 4. So like that. And this is a famous formula. This part goes to 1 as x goes to 0, so that the result is computed as 1/5. Any questions about this example? Okay, next. This is section 5.5. We will cover indefinite integrals and substitution method in this section. So let's start with the first one. We will be applying substitution technique. So how do we apply substitution? You choose some part from the function inside as your as your substitution will be some part from here. So let's try tangent x over 2 as our u. Then you will compute du. Computing du means you are taking the derivative. Secant square is the derivative of tangent function. Then you need to multiply with the derivative of the insider part like that. Okay. So then our aim is to rewrite this integral in terms of the new variable u. So you see this part here? This is what we see here, except this coefficient. So you need to send this coefficient to the left-hand side as the as 2 times du. So this part corresponds to du. And this part is, I call it as u to the power 7. So u to the power 7, 2 times du. 2 can be taken out, u to the power 7 du. So this is the usual power rule. You add 1 to the power, you divide by the same power. And as it is an indefinite integral, I need to add this arbitrary constant c there, because there are no boundaries. And finally, you need to do back substitution, meaning that you should turn back to your original variable x. Because our original question was in terms of x, you should give the result in terms of x like that. Okay? This is how you apply substitutions. Let's move to the next example. This one. Okay, we will choose some part as u so that the remaining parts will appear in du. This is how substitution works. Okay, we don't have much choice here, right? Either we choose this part as u or cosine as u, because if you choose 1/θ square as u, it won't help, because from its derivative, it is impossible to obtain sine or cosine. That's why either we choose this part or this part as u. So let's try sine, okay? Let's Choose this part as u. Sine 1 over theta. Now, du. Derivate. Cosine 1 over theta times the derivative of the insider part, which is minus theta square. And don't forget, put d theta at the end. You see, this whole part appeared in du, except this minus sign, right? So that is, in fact, minus du. This part corresponds to minus du. So let's rewrite the integral in terms of u's and du's. You see, it is, in fact, in this very simple form. It is minus, coming from minus here, minus u du, which is a very simple integral for us. It is a power function, add 1 to the power, divide by the same power. And plus c, because it is an indefinite integral. Now, time to back substitute. Our original question was given in terms of theta. That's why we need to turn back to theta variable. U was sine 1 over theta, okay? This is the final result. Any questions? If not, let's deal with the next. Okay, this time, before choosing your substitution, I think we need to rearrange the terms a bit because we have a very big power here which can be taken out from the square root, okay? So let's first try to decrease this power by taking it out of the square root. I'm sorry, this was not square but third. And what we have here is x to the power 8 times x to the power 3 dx, so that this integral is in fact x cubed minus 3. This can be taken out, so I will write 1 over x to the power 4, and x cubed is still there, like that. Next, here, integral 1 over x to the power 4 inside the square root. Now, instead of writing over a common denominator, I will separate into two parts. So it can be written like that now. And after this step, we will start applying substitution. Let's choose either this or this one as u. Of course, this one makes more sense because, I mean, inside the square root, you can eliminate it by choosing it as u. Okay, what is the derivative of minus 3 over x cubed? This is, in fact, minus 3 times x to the power minus 3. Take the derivative, minus 3 comes down, you subtract 1 from the power, so x to the power 4. So the derivative of this expression is, in fact, 9 over x to the power 4. Don't forget to put the x at the end. Okay, and then you see this is working because what we have here is, let me mark again, this part is exactly here, dx over x to the power 4. Just send your coefficient to the right-hand side. This is du over 9, right? So the integral becomes then square root u du over 9. So 1 over 9 can be taken out, integral of square root u du. Okay, this is in fact a power function, right? Square root u is u to the power 1/2, so that you can evaluate it as add 1 to the power, divide by the same power, and plus c, of course, because this is an indefinite integral. See, I see it as a power function and I applied power rule to take the integral, and then the final step is back substitution. So what we have here is you will substitute back. Sorry, what did I write here? I'm sorry, I should add 1, not 3. You should warn me on such silly mistakes. So add 1 to the power, divide by the same power, like that. So we have 3 over 2 plus c. What was u? Here u was 1 minus 3 over x cubed. Okay, so this is your final result. I substitute back. I turn back to my original variable x. Okay? That's it. Is that okay? Any questions?
It's clear.
Okay, next, let's deal with this example then. Okay, so we have this 10th power, and you can, I mean, it will be very long if we want to compute 10th power of this thing. Instead, we can call this part as u and try to rewrite the function in terms of u's and du's. Let's try it. X minus 1 is u, then du is dx, right? Derivative of it. Then our integral can be rewritten as, okay, this turns out to be as du, but about just x. You need to transform everything in terms of u's or du's. So is there a way to rewrite x in terms of u? You see, there is a way here. Yes, u plus 1. Then our substitution is working. Our integral is u plus 1, u to the power 10 times du. See, everything is transformed into u's and du's. Then this is simpler to compute, right? U to the power 10, you can multiply it with the left-hand side. Then what we have inside the integral, u to the power 11, u to the power 10 du. Now, time to integrate the power functions, add 1 to the power, divide by the same power. Add 1 to the power, divide. Plus arbitrary constant c as it is an indefinite integral. Then final step will be back substitution. We turn back to our original variable x. U was chosen as x minus 1. Okay, this is your final result depending on x. Any questions about the solution? Okay.
No, clear.
Thank you. So let's continue with this one. First of all, since we have some trigonometric function here depending on theta, we should think of transforming this 2 theta thing into theta by using half angle formula. Remember that formula, half angle? Sine 2 theta is 2 times sine theta times cosine theta. This is a trigonometric identity, so we are using it here. And then what we have, e to the power sine square theta d theta. Okay, this is our question now. We need to choose some substitution so that the whole remaining parts will appear in du. Obviously, I mean, you can see it after a few seconds that you should choose this part as u because take the derivative. 2 times sine theta times the derivative of the insider part. Derivative of sine is cosine. Don't forget to put this. See, if you choose this part as u, the whole remaining part becomes du, which is a very nice thing for us. So the integral is transformed to e to the power u du. That's it. That's simple. You know how to integrate it. Integral of e to the power u is itself, right? And then you will just back substitute. So the result is e to the power, turn back to your original variable theta, sine square theta, plus c is still there. Okay? Every time you need to put this arbitrary constant c whenever you have indefinite integral without boundaries. Okay? So is that okay? Can I move on?
Yes.
Thank you for the response. I am not alone here. Okay, this one. To evaluate this integral, there is only one choice to choose as u. It is so obvious. Of course, you will choose this part as u. And then you will compute du. I will leave the rest to you, right? Okay? This is an exercise. You will compute du and then you will try to rewrite your integral in terms of u's and du's and you will see. Next. Okay, this is an exercise for you. Let me continue with the next part. Substitution and areas between curves. Okay, again, we have an integral evaluation question. The only difference is it is not indefinite anymore. This is a definite integral. Definite means that we have boundaries. Okay. After noticing that, I also want to recall you something about the derivative of this inverse trigonometric function. It is arc secant x. Do you remember the derivation rule for that? It goes like 1 over x times x squared minus 1 inside the square root. This is the derivative of arcsecant function. After seeing this derivation rule, I think you understand which substitution we should take, right? If you choose this arcsecant part as your substitution, its derivative consists of the remaining part. Okay, then du is 1 over x times x squared minus 1. Don't forget dx. You see, if you choose this part as u, this whole part becomes your du. Then you transform your integral by using this substitution. You can transform your integral into your new variable u like that. Secant square u du. You see how simplified version we obtain. Okay, what about the boundaries? Can I write square root 2 and 2 here for the new integral? What do you think?
No, I think because it depends on x.
Exactly. These yellow shaded boundaries are the boundaries for x, you see? This integral is with respect to x. I cannot write them here as they are not the boundaries for u. We should find the new boundaries for u, okay? And how can we do that? We know the relation between u and x, right? If x is square root 2, you can compute u. If x is the upper bound, which is 2, you can find the value of u. Okay, let's compute the new boundaries of u for these values of x. Okay, arcsecant square root of 2 and arcsecant 2. How can you compute this inverse trigonometric function? You will just think in the following way. Tell me an angle whose second value is square root 2. Do you know such an angle? It's a famous angle. It is pi over 4. Similarly, tell me an angle whose second value is 2. It is also a famous angle, pi over 3, okay? So these two are now the new boundaries for u. And you have to write your new boundaries here. You cannot just directly use the boundaries for x. No, these are the boundaries for x, but my new integral depends on the new variable u, so I have to put here new boundaries for u, like that. Okay, time to evaluate now. Tell me a function whose derivative is secant square. Do you know such a function?
Tangent.
Exactly. Tangent u is the result of the integral. And now you can safely insert your new boundaries for u, right? So the result is tangent pi over 3 minus tangent pi over 4, which is tangent pi over 3 is square root 3 minus this is 1. So the definite integral, the result of the definite integral, definite means with the boundaries, should be a real number. This is first thing to remark here. Second, after you use change of variables, after you apply a substitution and apply a new integral in terms of u, you cannot directly use the old boundaries as they are the boundaries for x, not for u. You need to find out the new boundaries for your new integral, and then the rest is just straightforward computation, okay? Any questions about this solution? If not, I want to talk about now areas between curves. And here I want to start with a recall. Okay, so how do we compute areas between curves? Let's draw two different curves here. Let's say this is y equals f of x, and let's say this is y equals g of x. And I want to compute the area between these two curves corresponding over the interval a to b, okay? So I want to compute this shaded area. Okay, I want to compute this shaded area. Area between curves can be computed by using the integral. And we will integrate what? We will integrate the length of this line segment between these two curves. I'm trying to explain the idea why this integration, like this one here, corresponds to the area, that shaded area. Let me try to explain that. Okay, so f of x, the bigger curve, minus g of x, gives you the length of this line segment, right? And by putting the integral sign here from a to b, what you are doing, in fact, is to continuously sum all those line segments here, all those lengths of line segments. Remember, integration is a continuous summation. If you integrate such a length of this line segment, this means that you are summing up all the lengths of all line segments here. And you need to do a continuous sum from A to B to cover the whole area, right? And integration is a continuous summation. That's why the result of this integral will give you the shaded area, okay? So this is the idea. And now let's apply that idea by computing the shaded area given in the example. This, and this. Let's name this part as A1, this part as A2, A3. And for these three, A1, A2, A3, for these three parts, we will construct three different integrals, right? Why? Because the bigger and the smaller curve, bigger, and smaller curves are switching over these three intervals. That's why to compute the total area, which is A1, A2, A3, we need to construct three different definite integrals here, okay? So for A1, let's construct the first definite integral for A1. It is the integral of, bigger curve is the pink curve here, which corresponds to this. This is the equation of the bigger curve. This is the equation of the smaller curve. I mean, the blue curve. Pink curve is given by this equation, x cubed over 3 minus x. This is the bigger curve over A1 minus the smaller curve, which is x minus 3, the pink one. Dx, and the integral will be from -2 to 0, right? Over x-axis, the integral is from -2 to 0, plus for A2, this is A1, for A2, integral from 0 to this point. We don't know this intersection point now. Let's compute that intersection point. It is not given, we have to compute it. To compute intersection points, what do? We solve the curves together, right? Let's solve these two curves together. X cubed over 3 minus x is is x over 3. Like that. Now, take everything to the left-hand side to solve the equation. Minus 4x over 3. So you can take x over 3 out. Sorry, this is not cube anymore. It is square now, like that. Okay, and now I can see the roots. X is 0, x is 2 or minus 2. As we just can see here, x is minus 2 is the first root, 0 is here, and then this should be the x value of this intersection point should be 2 then. Okay, after finding out this, now we can construct the integral for the second part, a2. It goes from 0 to 2, right? This time, blue curve is the bigger curve, x minus 3 minus. Pink one is the smaller one. That's why x cubed minus 3 minus x. You should take the difference, dx. And finally, for a3, we will construct one more integral, okay? And it will, the boundaries of the integral will go from 2 to 3. Look at a3. Pink one is the bigger curve here. So x cubed over 3 minus x, pink one minus the blue one. Blue one is the lower boundary for that region, dx. So that's it. You can compute areas between curves if you know the equations of your curves and if you know the boundaries of your integral, like that. So by definite integral, you can easily construct some definite integrals giving you the area between curves. And the idea is like the following. Bigger curve minus smaller curve gives you the length of this line segment, and by integrating it over A to B, you are in a way continuously summing up all those line segments so that you are covering the whole area between the given curves. Okay, any idea? Sorry, any comment, any question? Then let me move on. Let's solve one example from this group. Let's solve this one. This time the graph is not given. There are similar questions. We will again find the areas of the regions enclosed by the curves, but the graph is not given, which was given in the previous example. It is not given here. We will draw the graph and then we will try to construct the definite integral. So 81, this curve is 4x squared plus y is 4. So y equals 4 minus 4x squared. Let's try to draw the graph of this parabola. It's a parabola and you can obtain the graph of it by doing shifting. So this is y equals 4x squared. You can reverse it like this to obtain the graph of y equals minus 4x squared. So minus is reversed graph. And then you need to add plus 4, right? Adding plus 4 corresponds to taking this curve 4 units up. So this is now the graph of 4 minus 4x squared, okay? By shifting, you can draw the graph of any parabola. And next, this one, x to the power 4 minus y is 1. So y is x to the power 4 minus 1. This is even easier because, you know, this is y equals x to the power 4 kind of parabola. Minus 1 means that you take this whole graph 1 units down. So this is minus 1. This is the graph of x to the power 4 minus 1. Okay. We obtain the graph of the parabolas. Let me draw them over the same coordinate axis so that we can see the enclosed area between these two curves. This is this first parabola whose equation is y equals 4 minus 4x squared. And this is the second parabola, like that. whose equation is x to the power 4 minus 1. Okay, this point is 4 and this point is minus 1. And as you can see, they intersect at these 2 points. To construct a definite integral for the area between these two, so let's shade the area enclosed by these 2 curves. We want to compute this area, and to construct the integral for it, we want to solve for the intersection points. Okay, intersection points. So how do we solve the intersection points? As usual, we will solve the equations together. X to the power 4 minus 1. Let's take everything to the right-hand side. 4x squared minus 5. And this can be decomposed into its components, right? X squared plus 5 and x squared minus 1. It can be decomposed like that. Here, we solve x squared as minus 5, right? Which doesn't make sense. So the roots will come from this part. X squared is 1, so the roots are 1 and minus 1. So these are the x components then of the intersection points. So this point is minus 1. This point should be 1, okay? After finding the intersection points, now we are ready to find the shaded area. It can be computed with an integral. So we need to look at this line segment. Bigger curve minus smaller curve we will apply. So the bigger curve is this red one, 4 minus 4x squared minus smaller curve. Smaller curve is given by this equation. Dx, what are the boundaries? And boundaries, we just find out the interval is this interval from minus 1 to plus 1, okay? If you compute this integral, you will find a real number as a result, and that real number will give you the area between these 2 curves, which is shaded like that. Any questions about this solution now? If not, before we stop, I want to show you one last example, which is this one. And before we start that, I want to put a recall here. You can compute areas between curves also by using integrals with respect to y. Remember, so far the areas is computed by the integrals with respect to dx, right? And we were using x boundaries here. You can take this metric story, you can change the roles of x and y, and you can still construct a definite integral with respect to y to find the area. So I will just draw the symmetric version. Okay, let me draw a curve like that. Let's say this is x equals g of y. Let me draw another curve. And let's say this is equation of this curve is given as x equals f of y. You see, I changed the roles of x and y. The equations are not given y equals f of x anymore. Instead, we are using the symmetric story. Consider symmetric story. This means that just change the roles of x and y. And we want to compute the area between these 2 curves. So I want to compute this shaded area now. The boundaries will come from the y-axis, not x, but y. We are completely consider the symmetric story. So this shaded area can be computed by a definite integral, which will be computed in terms of not x, but y, okay? That's why the boundaries are the boundaries coming from y-axis, from C to D here. over this interval your area lies. And now the bigger function is, which one? F of y is the bigger function, having bigger values in terms of x, minus the smaller curve is g of y now, okay? Now you are thinking not vertically, but horizontally. Now you draw your line segment horizontally. So this is the length of that line segment, bigger minus smaller. So you can also use these horizontal arguments to compute the area between your curves. It is up to you. You can either use this vertical setting and take the integral with respect to x, or you can use this horizontal setting and take the integral with respect to y. Okay, so let's look at the example. There is a shaded area here. We want to compute the shaded area by using definite integrals. First of all, let's find out this intersection point. It seems like it is 1, but not so sure. Let's verify that. The given intersection point is 1. Okay, intersection point. We will solve the given equations together, that's all. Y minus y squared and, sorry, it is the pink one. These are the intersection of blue and green one. So 3 minus y is 2 square root y. Let's solve them together. Let's send everything to the right-hand side. Y plus 2 square root y minus 3. You can decompose this equation as square root y plus 3 square root y minus 1, right? Then you solve, there is just one real root of this equation because square root y equals minus 3 doesn't make sense. The result of the square root cannot be negative, but this makes sense. Square root y is 1, means that y is 1. So this intersection point has this y component 1. We just find it with computation. Now the shaded area. This area should be divided into 2 parts as A1 and A2. We will be using horizontal setting to find out the areas as definite integrals. So in this horizontal setting, we will be using this idea, but why I divided the shaded area into 2 parts? Because the bigger curve, smaller curve, bigger curve, smaller curve. Bigger and smaller curves are different for A1 and A2. That's why I cannot cover the whole area in just one single integral. I have to construct 2 different integrals for A1 and A2, right? Okay, the shaded area is given by A1 plus A2. Next, the integral for A1 is, the bigger curve for A1 is 2 square root y minus the smaller curve. Smaller curve is in fact y-axis. The equation of y-axis is x equals 0. Okay, dy. What are the boundaries? Look at the y boundaries. Look at the interval over which A1 lies. It is from where to where? 0 to 1. Again, next, this, by the way, this expression gives us the value of A1. Now, for A2, start constructing your definite integral. For A2, the bigger curve is this green curve, smaller curve bounding A2 is this pink one. So bigger one is 3 minus y minus y minus 1 square is the smaller one. Y minus 1 square dy. Be careful, we are using this horizontal setting. That's why all the integrals will be with respect to dy. And all the equations of the functions will be in terms of y, just like given here. So look at the y boundaries for the second part, this part. A2 lies over this interval, which is from 1 to 2 on y-axis. That's why boundaries of A2 is from 1 to 2. Okay, so that's how you should construct definite integrals in the horizontal setting. And you should use boundaries from y-axis. You should find the boundaries for y. Okay, and the rest is just computing the definite integrals. I think you can easily do that, right? This is a power function. Okay, let's do that quickly. This is y to the power 1/2. So you will add 1 to the power, divide by the same power, and then you will insert these two numbers and take the difference. Plus the second, this is the result of the first integral. Let's also evaluate the second integral. How do you evaluate it? You first evaluate the square, y square minus 2y plus 1. And here it goes. 3y is the integral of 3 minus y square over 2, integral of the second expression, minus, add 1 to the power, divide by the same power, minus, minus, plus, integrate, add 1 to the power, divide by the same power, minus y. So this expression is the result of the integral. Then you will evaluate this expression for the upper lower boundaries of y. Okay, so I will leave the insertions of upper lower boundaries to you. At the end, you will find a real number here, which will give you the result of the shaded, area of the shaded part. Okay, that's it. Any question about this solution? You can also compute the areas in the horizontal setting where your integrals should be in terms of y, not x, but dy is used here, right? Okay, that's all I wanted to tell you this week. If no questions, I will stop. Any questions? Okay, thank you for your attention.